In this video, we're going to talk about how things dissolve in water to make aqueous solutions. We're going to look at an atomic view of how water molecules dissolve solute particles, which is a process known as solvation. And we'll see that solvation occurs differently for covalent and ionic solutes. Let's start by making an aqueous solution, one that you've probably made yourself many times. We'll dissolve a sugar cube in water. So here, sugar is a solute and the water is the solvent. We're making an aqueous solution of sugar. Now, if you've ever dissolved a sugar cube in water, you know it takes some time to dissolve. It's not instantaneous. Let's take a closer look at what's happening during this dissolving process. Here's our sugar cube. And let's imagine that we could zoom into it many times and see the atoms and molecules. We'd see that the sugar cube is made of trillions and trillions of molecules that look like this. Table sugar is actually a compound called sucrose. Here's its chemical formula. And it's made of carbon, hydrogen, and oxygen atoms. Because these elements are all nonmetals, you know that sugar is covalent. Its atoms are connected by covalent bonds made by sharing electrons. And there are different ways that we could show the molecule. So here, we're representing the sugar molecules with a 2D Lewis structure that shows the covalent bonds. If you made this into a ball and stick model, it would look like this. But a more accurate depiction of sugar is actually closer to this. We call it the 3D model. It's a bit blobby and kind of hard to see all the different atoms. But we're going to use this model for now because it will better illustrate what we're talking about here, which is how molecules interact. Now, let's look at water, which is our solvent. Water has a chemical formula of H2O, and here are some 3D models of water molecules. Now, we want to look at dissolving here. So let's zoom in on our sugar cube in the water. We're going to look at this edge right here. So here's the edge zoomed in millions and millions of times. The sugar molecules are all clumped together. This looks pretty confusing, so we're going to clean it up a little. We'll reduce the number of sugar molecules and we'll arrange them in neat little columns. See? This is easier to look at. But just remember, things are more messy in real life. Also, remember that this sugar cube is sitting in water. So now let's add the water molecules that are on the edge of the cube over here. There we go. We got the water and the edge of the sugar cube. Now, for the water to dissolve the sugar, water molecules have to bump into the sugar molecules. They got to bang into them, sort of like this. And they can only do this at the surface of the sugar, so it takes some time. Then, after bumping into the sugar, the water molecules kind of work their way in between the sugar molecules and surround them. You can see that happening here. Once a sugar molecule is surrounded by water molecules, they carry it into solution. Here, you can see that one of the molecules of sugar is surrounded by water molecules and it's carried away. Now, keep your eye on this one here at the top, and there we go. It got surrounded and carried away. As the water molecules carry the sugar molecules into solution, new water molecules can reach the undissolved sugar over here, and the process continues. I think this one's next, and there we go. Another one gets surrounded and starts to float away. And this is what's happening at the atomic level as sugar dissolves. All these sugar molecules are coming apart from each other, and they're getting surrounded by water molecules, and they're floating off into the solution. Now notice one thing here about how the sugar molecules float away. This is super important. The sugar molecules separate from each other, okay? But the whole molecule stays together. The molecules don't break apart into their atoms. In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule. The atoms in the molecule stay together as the sugar dissolves. So, as you can see, we have 3 molecules that have come off the surface so far, and this process will keep happening, pulling more and more sugar molecules into the solution. Let's zoom back out and look at our glass. And here we are. We were just looking at one side of the cube, but this dissolving process is happening all over, on all the different sides, anywhere that's touching water. Now, after the dissolving is complete, all the sugar molecules will have been pulled away from the cube, and the cube is gone. And if we could zoom in and look at the liquid here, we'd see that the sugar molecules are mixed in with the water molecules, spread all throughout. So this is what a solution of sugar dissolved in water would look like at the atomic level. Now, as we've seen, a big part of dissolving is that molecules of solute get surrounded by molecules of solvent. There's a special name for this process. We call it solvation. And we use the term solvated to refer to solute that is surrounded by solvent molecules. Now, if the solvent is water, like it is here, you can be extra precise and you can say that these molecules are hydrated. When we say a solute particle is hydrated, it means the same thing as solvated, but we know the solvent is water. These little clusters of water molecules surrounding a solute particle are called hydration shells. You might also hear them referred to as solvent cages. They make this little cage or shell around the solute. Just keep in mind that they surround the entire solvated particle, so they're actually in 3D, right? Even though we're just drawing them in 2D here. So that's hydration shells or solvent cages. Now, let's switch gears here and see how ionic compounds dissolve. Sugar, which we looked at earlier, that's a covalent compound. But the process of solvation works differently for ionic compounds like sodium chloride or table salt. We know that sodium chloride is an ionic compound because it's made of a metal, sodium, and a nonmetal, chloride. Here's a grain of salt. If you could zoom down to the atomic level, you'd see that a salt crystal is made of trillions of tiny ions all packed together. Sodium ions have a positive charge and chloride ions have a negative charge. These ions are bonded together by electrostatic attraction. It's kind of like trillions of tiny magnets all stuck together. So, let's see how solvation happens with an ionic compound. We'll zoom in to get an even closer look. When you put sodium chloride in water, the water starts bumping into the ions at the surface of the crystal. And then the water molecules surround the ions and pull them apart and carry them into the solution. Now check this out. What we're seeing here is that for an ionic compound, the individual ions get pulled apart during dissolving. This is different from what we saw with sugar. This process, we call it dissociation. Dissociation is how ionic compounds separate into ions in solution when they dissolve. So, when salt is dissolved in water, it dissociates, it comes apart into ions. Let's zoom out here. Remember that dissolving happens all over the surface of the salt. Once a dissolving is complete, the ions are spread throughout the water. So let's stop to compare how water dissolves the 2 different compounds that we saw. Sugar is a covalent compound. It's made of molecules. When sugar dissolves, the molecules move away from each other into the solution, but they remain intact. The water doesn't break the bond between the atoms in each molecule. But on the other hand, salt is an ionic compound. It's made of ions. When it dissolves, it dissociates, it splits apart into positive and negative ions. Now, let's look at dissociation here a little more closely. One thing you might have noticed about the diagram is that the water molecules are surrounding the ions a bit differently. For sodium, their oxygen atoms face the ion. But for chloride over here, the hydrogen atoms are facing the ion. Why does water form these two different types of hydration shells? Well, we have to mention something about water here. You may know that water is a polar molecule. That means that a water molecule has partial charges, very weak electrical charges at different ends of the molecule. The two hydrogens here are partially positive, and the oxygen is partially negative. These polar charges are much weaker than full charges on ions, but they're still important. This polarity has an effect on solvation. The partial charges are attracted to the ions. When water molecules approach a positive ion, like sodium here, the partially negative oxygen is attracted to the positive ion because opposite charges attract. And the partially positive hydrogens are repelled because like charges repel. The exact opposite happens when water molecules approach a negatively charged ion like chloride. Here, the partially positive hydrogens surround the negative ion like this, and the oxygens are repelled by the negative ion because they have a partial negative charge. This pattern also shows why water is so good at dissolving ionic compounds. The partial charges are attracted to the ions, the water surrounds them, and then carries the ions into solution. Now finally, we've seen that the sugar molecules dissolved in water are organized differently than the sugar molecules in a sugar cube. And sometimes it's important for chemists to show the difference between a substance when it's solid and when it's dissolved in water. We can use state symbols for that. State symbols tell us the state of the chemical. For instance, here is the formula for sugar. If it's solid sugar, we can add S. But an aqueous solution of sugar gets the AQ state symbol. The same goes for salt. When you have solid salt crystals, it's an S. Salt dissolved in water, AQ. Just remember, when an ionic compound dissolves, it dissociates into ions. So NaClAq actually means Na plus AQ and Cl minus AQ. So, we've seen how aqueous solutions are made using covalent and ionic solutes. The water molecules bump into the particles of the solute, knock them loose, surround them, and carry them into solution. This is called solvation. If the solute is covalent, the solvated molecules remain intact. But if the solute is ionic, the water causes the compound to dissociate into separate positive and negative ions. When particles are surrounded by solvent, we call them solvated, or we can call them hydrated if the solvent is water. Water molecules surround ions in particular patterns because the partial charges on water are attracted or repelled. And finally, we can use the state symbol AQ to show when something is dissolved in water to make an aqueous solution.